Okay, now, if you have followed me from, I should say, the previous course which I had on the Bayesian modeling, especially with the regression analysis that I used the standard ARM package inside the R, you should remember probably that the datasets that we used for our modeling was the women datasets. Essentially, we saw that we had 15 pairs of the women's, that for each pair we had, for example, we could identify each woman, if I can call it, for example, with the A. We had, for example, the woman was recognized, I should say, by a pair, which the X was represented by the weight of that woman, and the Y coordinate was essentially represented by the height. The thing that we did over there, we said that, okay, if I consider this one as an X, and I take this one as a Y, then the thing that we did was essentially like that. We said that we are just going to try to make this model as a kind of a linear model that we did. We tried many different models. We tried from the linear to non-linear, and we tried many different, I should say, fitting in order to achieve the best accuracy of the model that we were looking for. We said that we can just come here with this model. We said that, okay, imagine that if you look at this basic equation, ax plus b, which is going to be the basic linear function that we could have thought of it, we could have come here to say that, okay, in that case, we can say the height is going to be equal to slope A times weight plus B. Remember that from that method that we used in the Bayesian with the R modeling that we did, we said that we call A and B as slope and the intercepts, and the main target that we had when we were looking at this model was that try to make an inference and the best estimate for these two values. We tried two different methods. The first method that we tried, it was a non-Bayesian context that essentially we tried ordinary least squares, I should say, optimization process in order to minimize the, I should say, the sum of the squared errors that we had from that model. And also we tried within the Bayesian context, but from the Bayesian context we essentially didn't do the optimization process. Essentially we did some kind of samplings from the parameter space that we just had the model as a dynamic Hamiltonian Monte Carlo. It was all the things that we did. And now when we just want to just do the same thing, but essentially use the standard programming language, which is not as an interface, it has an interface with the R. We tried the R stand ARM, but now we just want to use the stand itself. The crucial thing here is that we have to just have a model before we just go on and start to write our very first program, I should say, in the stand. And the thing that we have to do is this. The model that we created for the women's height and weights, which essentially is going to be this, this model is going to be replaced by somehow similar, however, it is going to be somehow similar instead, but with a different, I should say, notations. What do I mean? I mean that we just come here and say, okay, height is going to be represented by a distribution. We can say that, for example, the distribution that we have, it's a well-known distribution. We say that we can also check that. We can say that, okay, it's going to be distributed normally. And we say that this normal distribution has two, I should say, parameters. The first one is going to be defined as nu. And the other parameter, which is crucial, is going to be the sigma, which is going to be a parameter for the dispersion. And now please listen very carefully to this part. And now here is our story is going to start, because now here we are going to see that what do we mean by the parametric Bayesian. And now here it should just make sense to you that why do we call that a parametric Bayesian? Why? Because look at that. For the normal distribution, that we said that it's going to be our assumption that our heights are going to be, I should say, represented. We come here and say that the nu that we talked about, the nu, which it was the mean of a normal distribution, now it's going to take, as a parameter, it's going to take a function, that this function, that's the thing that we have to just, I should say, put that within the stand. Then as a result, we can come here and say that, okay, now the linear program which we talked about, which is going to be A, for example, times weight, plus B, is going to come as we can see from the parameter nu, which is going to be called, let's say, for example, it's going to be called the average of our parameter is going to be taken into account. Let me pick up a good color. Let me take this color. Okay, now this is essentially is inherent with the name which is called, I should say, the mean. The parameter which was supposed to be the mean, now it has this equation. And as what we have done before, again the same story opens here. We have to find the best estimates for our slope and intercepts. However, the program, the method and the methodology that we're just going to have here to make the best estimates for the A as in slope and B as an inference is not going to be as the same as we did on the non-Bayesian context. In the non-Bayesian context, we used the least ordinary least squares method. I'm just going to write it, ordinary least squares method. But here we say that, okay, in order to find the best estimates for the A, I'm just going to go to the next page. We said that in order to find the best estimates for the A, which A was essentially our, for example, our slope, in our linear model, we say that in the Bayesian process, we said that the A is going to be essentially the mean of the inferences that we are just going to get from the posterior that we have just made. And now with respect to, for example, the parameter which has defined, for example, the A in our model. For example, if A is going to be the intercepts, and this is going to be essentially represented as, for example, you're going to see that I'm just jumping a little bit ahead, but it's good that you can just see that the key difference between the non-Bayesian parameter estimations and the Bayesian parameter estimation, you see that the main difference is going to be the mean of the posterior, that we are going to extract the value, the parameter in our model which defines A. For example, you're going to see that the A, which is going to be the slope, for example, you see that it's going to be defined as, for example, the beta as a parameter in our stand programming. You're going to see that very soon. And now I'm just jumping a little bit ahead. Maybe that's a good thing that you see the main difference before we just go on to just jump in to do some kind of programming. And now also as an intercept, let me just go ahead. The B, which it was essentially our intercept, the B in our model is going to be the intercept. The B, essentially this one within the Bayesian framework, is going to be the mean of, again, the posterior. Essentially it's going to be the posterior, which we are going to extract from it the parameter which defines the intercept of our model. Please listen to that carefully. When we just go to the R environment, try to just write our first model, you're going to see what do I mean then. For example, in your programming language within the R and R stand, you may decide to describe and name your intercept, which we called it here B. You may call that as an alpha, for example, or gamma, anything. It depends on what you prefer to call that. I'm just going to call that, for example, alpha. Because alpha is a parameter describes, I should say, the intercepts within, I should say, the R on R stand, then you see that in the Bayesian framework that we have, and within the stand, things is going to be a little bit different than what we had before with the R stand R. In the women data sets that we had, that we said that, for example, we can describe each woman's as an X referring to its weight and Y referring to its height. We said that we can just model the dependency of the height with respect to the weight. If we say that there is an alternative hypothesis that we can just come with an inference with the A and B, then we say that there is a relationship that we can just model that in a linear model like that. And if we did that in, let's say, within the non-Bayesian context like this. However, when we just go to the stand, which is a language of the Bayesian, that we just make our best estimates and inferences based on the dynamic Hamiltonian Monte Carlo, a variation, I should say, of the MCMC, we see that in order to describe the mathematical equation, we do not say height equals to, for example, A as an intercept multiplied weight plus B. We have to first come that height is going to be described by a probability distribution, which we look at that as a normal distribution, which a normal distribution is defined by two parameters. Mu, which describes the average or the central tendency of the heights when they are distributed with respect to the X, and also the sigma, which is a measure of the dispersions around, I should say, the central tendency. In the model, normally we come with a clear-cut, I should say, value for the sigma. However, we normally come here for the nu, we define it as a parameter. And parameter, that's the thing. That's why with the method, which is called parametric Bayesian, comes from this part of this methodology. That are, for example, our mean of a normal distribution is not clearly and explicitly defined for you. It is a kind of a parameter, like the parameter equation that I have a plot of it here. And now we have this, for example, nu, the average, is now it's that functions that we thought of that before, which is going to be A times weight plus B. You can come, for example, with, let's say, with a quadratic or cubic function as we did on my previous course. But now we think that a linear function should be fine to describe, I should say, should be fine, the linear function should be fine to describe the parameter, which is going to be this one. And essentially, before we just finish this tutorial, I said also, I'm just recapping what we did. I said that in the non-Bayesian context, in order to find the best estimates for the slope and the intercepts, was the ordinary least squares method. Try to minimize the sum of the errors that we had. However, with the Bayesian frameworks, we do not have an optimization method. We have samplings from our posterior distributions within the parameter space. Now, then as a result, in order to find the best estimates for the slope, we come here to extract the posteriors and extract the distribution which defined, for example, my slope. For example, it can be beta. When we just go to, I should say, to the practical things in action, you see that what does it mean? And now take the mean. We take the mean. That's what I want to emphasize here, that the mean is going to be crucial. And in the next tutorials that we just take the means, I hope that you understand why do we take the mean from the extract that we had from the posteriors with respect to the parameters. And also for this intercept, the same thing. We take the mean of the posteriors that extracted from the, I should say, the variable which described, I should say, are, for example, the intercepts in the model then. Okay, I think that was a very good start before we just move on to just do some kind of codings in the R. Especially, I just wanted to highlight the key differences between the non-Bayesian and the Bayesian, and also the main thing that we just take the mean of the posterior distributions rather than just thinking of an optimization processes then. Okay, I hope that it was a good session for you also, and I see you on the next tutorial.